Welcome to a little lesson on rates of reaction. Now, so this is the A2 material that we're going to be looking at, so it involves a little bit more maths than the AS. So as you'll remember from AS material, the rate of reaction is the rate of change of amount or concentration of reactant or product, and normally our units would be moles per decimeter cubed per second. Now, for a rate equation, which is what we're going to introduce at A2, you cannot use the equation to predict it. So if we've got A plus B going to C, our rate equation looks like this. So our rate is equal to our rate constant, which is a little k, times the concentration of A raised to some power, let's call it m, times the concentration of B raised to some power, and let's call that n. So really important, use square brackets because that tells me we're looking at concentrations of A and B. The rate constant we'll come back to in a minute, but the rate constant is dependent upon temperature, and m and n are exponential values. So in order, the overall order of the reaction is m plus n. You add them together. The order with respect to A is m, and the order with respect to B is n in this example. And for A level, m and n can be 0, 1 or 2. If it's 0, then that expression disappears because anything to the power of 0 is 1. So that means that the concentration, if m in this example was 0, it would mean the rate would not be dependent on the concentration of A at all. We have to find m and n experimentally. We can't use the balanced equation for this at all. So here are a few definitions that you should learn. So the rate constant is that little k, lowercase k in the rate equation. It's a constant for a particular reaction at a given temperature, but it is highly dependent on temperature. The half-life, if you do physics, you would have come across half-life before, but half-life of a reaction is the time taken for the mass or concentration of the reactant to fall to its half initial value. So let's say the concentration of HCl starts at 1 mole per decimeter cubed. The half-life would be the time taken for it to go to 0.5 moles per decimeter cubed. And the rate determining step, which we'll look at in more detail later on, is the slowest step in the mechanism. So think back to your organic chemistry. You often have mechanisms that have 2 or more steps. They won't all happen at the same speed. We'll have a look at that a little bit later on. The rate determining step is the slowest step in that mechanism, and that's the one that determines the rate equation. So, as we talked about a little bit earlier on, you have to do an experiment to find these orders. And one way to do it is to use a concentration time graph. And this is where you just mix the chemicals together and you record the concentration of one chemical over a period of time. You then plot the graph and draw tangents at several points to find the gradient. And the gradient gives you the rate at that point. So let's look at an example. So let's say this would be the concentration of a product. Why do I know it's a product? Well, because the red line you can see is getting bigger, it's getting larger. So this is the concentration of a product being produced over time. And you can see that around this area is actually stopped. So this first tangent, which has been drawn at time equals 0 there, that would be actually the initial rate, which we'll look at in a minute. So you draw the tangent and then you measure the y distance divided by the x distance. So that's y, that's x, and y divided by x is equal to the gradient. So for each of these values, you would divide y over x, and this would give you 3 points. So 3 rates at a certain time. So this would be at time equals 0, that would be at that time, and that would be at that time. And from that, you can then determine the order with respect to the reaction. Here is the concentration time graph for another reaction. And this is a very special reaction. So I am plotting the concentration of reactant A falling as the reaction proceeds. Hopefully you can see that each of these, so I've gone from 4 to 2 there, and that there is my half-life. Equally, I've gone from 2 to 1 here, and that distance is the same as is that distance. So for this one, it's a constant half-life. The time taken for the concentration to halve for reactant A is always the same. And in this case, it takes 17 minutes to do that. If you find a graph, if you plot a graph like that, this means that the order with respect to A is first order. For any first order, the concentration will always have a constant half-life. So this gives you a little shortcut. Okay, but let's say you haven't found one with a constant half-life, so it could be either first or second order, but we'll also do it for first order as well. So you've taken your tangents and you've calculated the rate at certain concentrations for each reactant. How can you now tell what the order is? Well, if it's zero order, as the concentration changes, it has no effect on the rate. So it is just a line parallel to the x-axis. If it's first order, it's a straight line starting at 0, 0, going up like that. So it's a fixed gradient. And the gradient of the line is equal to the rate constant for the reaction. If it's second order, the rate is proportional to the square of the concentration, so it looks something like that. So, just in summary, the blue line is zero order, the red line is first order, and the green line is second order. So once you've done your gradients, you've got rates at different concentrations, you can plot a rate concentration graph and you'll be able to tell from there what the order is with respect to that reactant. The other way that you can determine the order with respect to each reactant is to do initial rates. So you find you take the rate at time equals 0. So you add all the chemicals in, you find the rate, the initial rate at time equals 0, and then you'll be able to work out the rates by using different experiments. So for this example, we've done 3 experiments. Experiment 1, we had concentration of 0.15 for A, 0.15 for B, and we found an initial rate of 1 mole per decimeter cubed per second. And we then changed the concentration of A in experiment 2, and then we changed the concentration of experiment B in experiment 3. And obviously each time the rate changed. So how will this tell us the rate, the order of reaction? Well, if we look at experiment 1 to 2, you can see that the concentration of B has remained the same. However, the concentration of A has doubled. What's happened to the initial rate? Well, it's gone up by 4 times. So that would tell me that if I times the concentration of A by 2, the rate goes up by 4, which is 2 squared, and therefore the order with respect to A is second order. What about B? Well, in experiments 1 and 3 now, you can see that the concentration of A has stayed the same, the concentration of B has doubled, and the rate has doubled, and therefore it must be first order with respect to B. So now I've done that, I can work out my rate equation. So the rate is equal to little k, the order with respect to A we said was second order, and the order respect to b was first order, so we don't need to put a number there, and that is my rate equation for that reaction. And now often you'll have to calculate the rate constant k, so you need to be able to rearrange that equation, and in the one that we've looked at, if I find, to find k, it's the rate divided by a squared b. Okay, and if you put some numbers into that, when the rate was 1 mole per decimeter cubed per second, the concentration of A was 0.15 squared, and the concentration of B was 0.15, like so. So if you do that, you will end up with K being 296. But you need to think about your units here. Rate is in moles per decimeter cubed per second. Concentration is in moles per decimeter cubed. And I've got three expressions of that. So that will cancel and that will become squared like so. So your units become moles to the minus 2, decimeters to the power of 6, and then seconds hasn't changed to the minus 1. So the rate equation tells us about the molecules involved in the slower step in a mechanism. So from our example that we've just done, I know that in the slower step will involve 2 molecules of A and 1 of B. 2 of A because A is squared, and just 1 of B because it's first order with respect to B. So if this is my overall equation here, and I know that in the slow step it involves 2 molecules of A and 1 of B, that could give me a particle of C and some intermediate X. Now X doesn't appear in the overall equation, so I need to get rid of that in the next step. So that could be X plus B gives me D. Now if you add these two equations together, you will see it becomes 2A plus 2B goes to give me C plus D, like so, and X cancels out. And for this one is slow and this step is fast.